Okay, so let me continue to talk about slide 22, how to find the t-test value. So we just simply Google it. So for example, t-test, degree of freedom equals 28. Then you will see a lot of sites, and let's click this first one. All right, so here we see the table. And our t-test degree of freedom is 28 here. So this column shows 0.95 is 95% and confidence. 0.05 is rejection area. So in this normal distribution, so this both sides belongs to 0.05. Okay, so since this is two-tailed test, we follow this one. That's why it shows this two sides yellow highlighted parts. Okay, so t-test, when you find out a specific t-test value, you need to know the degree of freedom here. And then you have to know the alpha criterion value is also should be known, 0.05 here. So 28, degree of freedom 28, alpha 0.05, and you will see the test value, t-test value is 2.048. Okay, so let's go back to this. So that's why this value is found in that way. So it's nothing important. Just we simply Google it and find out the test value, okay? And then how can we derive the B1 slope? So this is B1 star, which is beta weight. But the original formula for B slope is R times Sy over Sx. So this is standard deviation for Y, standard deviation for X, right? So what does that standard deviation mean? It means standard deviation become 1. So since this values, since this value is 1, so now B equals R. So if you want to make, if you, I mean, in the simple regression, B1 star is the same as R. But in multiple regression, we do not have this formula in the multiple regression because we have a multiple B1, B2, B3, something like that. So this formula is only working well in simple regression. Okay. Likewise, t-test value is going to be the same as the f-test value. I mean, accurately speaking, is not the same because t squared t is the same as f in the simple regression. But t squared t is not going to be the same as the f-test in multiple regression. Okay. So here, 4.53 is our t statistic. And before, when we have a 28 degree of freedom, we got this t value, which means this is critical value criterion. Then we compare this value and this value. So our t is this, and this is criterion from the table. Since this t is larger than this critical value, we conclude it's statistically significant, which means we reject the null hypothesis. Okay, so this is the second technique, second method how to test the hypothesis. So number one method is p-value method. So if p-value is smaller than 0.0 alpha, 0.05, as alpha, it is statistically significant. And second method, if your t is larger than critical value, whatever it is shown in the t distribution table, it's statistically significant. Okay, and we at that time we reject the null hypothesis. So what is null hypothesis? Correlation is 0. So we reject that. That means the correlation is non-zero. Am I right? Okay, so when you have like this high value of t-test, then your p value is that much small. This very small value, so this is smaller than 0.0 alpha, right? Yeah. So we conclude that there is a non-zero correlation between SAT and GPA in the population. So R was 0.65, R square is 0.43. So this is much higher than 0.25. According to the Cohen's rules of thumb, 0.25 is regarded as a larger effect size, R square. Do you remember that slide? Yeah. So since we have only one single variable in the simple regression, beta 1 equals 0 is the same as correlation rho equals 0. This correlation is between what and what? Y and Y hat. Between Y and Y hat. So estimated Y and observed Y. So they are the same. If the correlation between two is 0, means your model is not good. Okay. So this is the same as this, means this model is simple regression model. Okay, only one X. Likewise, beta 1 equals 0 means your beta is 0, no effect on the Y outcome. Okay, it means your slope is 0. Your slope is 0 means your regression line is flat. You remember the XY coordinate. Your line is slope is 0 means that your line is flat. Okay, if that happens, SEE is very close to standard deviation of Y. SY is the standard deviation of Y. SEE is the standard error of the estimate. So standard deviation of sampling distribution. So do you remember CLT that I was talking about? Central limit theorem. All right, so don't be afraid of this kind of mathematical formula. This is simple, and also you don't need to memorize this formula at all. So this is the standard error of slope. How do we calculate that? Is numerator is the standard error of estimate, and denominator is the standard deviation of X, and you need the sample size here. Okay, this is called sum of square X. So sum of square X, then root. Okay. Anyway, S standard error of slope equals SEE divided by root SSX, sum of square error. Sum of square errors. SSX is the sum of square X. Our t-test will be t equals this numerator divided by standard error. So do you remember the null hypothesis, beta 1 equals 0? So t-test B1 over SB1, okay? What are SEE and SSX? So SEE is the standard error of estimate, and it's the standard deviation of the residual around the line, the vertical line. Also called the root mean square error, mean square errors. It can be computed several ways. So I provide the conceptual formula as well as the computational formula. Sometimes we do not have all the numerical values to calculate the conceptual formula, but if we have alternative values there, we still can calculate the value using computational formula. That's why I try to provide a bunch of different types of formula here. Here we have sample size and number of predictor and R. Then standard deviation of Y. Then we can calculate standard error of estimate. What is the standard error of estimate? It's squared MSE, mean square error. And this is error part, and then this is degree of freedom for error. So we use this, okay. Well, actually, this slide says you don't need to worry about it. Yeah, don't try to memorize the formulas. Just try to be accustomed to this. But well, even though you don't understand these here, you don't need to worry about it. This is the last time you see this slide set. SSX, sum of square of x. So this part, x minus x bar means mean of x, and then square, sum of square, okay? Observe the value minus x bar. Observe the value minus x bar, okay? SSX n minus 1 times, this is the variance of x. So mathematical statistician already proved this formula. So we just borrow the formula. So how convenient, how convenient. So we just apply this formula to our data analysis. That's it. Okay, so standard error for slope is this. So because this is numerator, this is denominator, we can find out some relationship among the numerical values. For example, when do we have a small standard error for slope? So the numerator is small, standard error becomes small. Denominator large, standard error becomes small. So what is the denominator? Sample size times, kind of this part is the sample size portion, and this is the standard deviation of x. So if your sample size is large, this whole number becomes small. So whole number is the standard error of slope, okay? If you have a larger sample size, that means your standard error for slope becomes small. Your error becomes small. That means your accuracy, your precision becomes higher. So that's why I advise you to have enough number of sample size in your data. So SBS, standard error for slope, is the estimated value of the standard deviation of a hypothetical large set of slopes. Standard error for slope is the standard deviation we would get if we sampled repeatedly from the population of interest. So I already told you, like one jar has 10,000 bowls, and then you get 100 sample means, right? Yeah. So we would like standard error for slope to be small because it means we have a precise estimate of slope in our sample. Now, T formula. So the numerator part is B1 statistic minus beta 1 parameter. Since our null hypothesis is set as beta 1 equals 0, this becomes 0. So then what happened? B1 over standard error for B1 is the same as T. And standard error is converted into this way. And this part becomes numerator part, okay? So t-test, if t-test is high, it means you are likely to reject the null hypothesis. So still p-value and t statistics connected each other. And last method that we do hypothesis test is the confidence interval method. So in this formula, 95% confidence interval for beta 1 slope, parameter slope. So P1 is sample slope plus minus T statistic, and alpha over 2 means two-sided test, two-tailed test. And this part is for what? Standard error part. So this term is the error part. This term is for kind of true part. So you will have like an interval, lower bound, upper bound. So as long as your true value here, as long as your true value belong to this confidence interval, you fail to reject the null hypothesis. And if the confidence interval doesn't capture zero, you reject the null hypothesis. That means your slope wouldn't be 0. Does it make sense? So this is the example. This is an example. So B1 is given with this number SEE and SX. And based on this formula, you got the standard error, 0.001. And now you plug this number here, and then B1 is here, then you got 4.53. This is higher than critical value, T, critical value. So we reject the null hypothesis. And now confidence interval method, you have a standard error, this guy here, and this is what, 2.05 critical value, and this is B1 slope. And now your upper bound is 0.007, under bound is 0.003 for the confidence interval. So this does not capture 0, so we reject the null hypothesis, which is the same result as this. T, according to the t-test value, we reject the null hypothesis. Do you remember that? Yeah. So all the three methods for hypothesis test, draw the same result, rejecting the null hypothesis. Am I right? Now, what about the R square? R square. So R square shows model summary. Okay, so the formula is R squared equals SSR over SST. So SSR is the sum of square regression, so explained part by the mother. And SST is the entire variation. And some people call SST, or some people call SSY, Y. So total variation, the denominator is a total variation. And SSR is explained variation by the mother. So sum of square total is equal to SSR plus SSE. Sum of square regression plus sum of square errors or residual. Okay. And SR, R square is the proportional explained variation over total variation. So some people, some people can be confused with this formula very often. I saw that kind of occasions. SST is the sum of SSR plus SSE. R square is proportional variation. So the numerator is explained part, and SST denominator is total variation. So you wanna have a higher number of R square, right? You wanna have a higher sum of square regression. So you can read this definition. And beta weight is how well each independent variable explains. R square is how well all of the independent variables are working together to predict the dependent variable. So if you have a 40%, 0.4 for R square, this means that 40% of the variation in dependent variable is explained by the mother. The mother means all the X variables. So since the explained part is 40%, unexplained part is 60%, right? Because the maximum is 100%. Okay. So some people, feel like, okay, unexplained part is 60%. It's so high. So I would say like this 40% of R square is not that good. Yeah, some people might say that. But generally, if one variable explain the outcome variable with this 40%, that means that explain a lot. So also, do you remember the Cohen's rules of thumb? R square, as long as the R square is larger than 0.25, it's really kind of large effect. So this this 0.4 is larger than 0.25. So this is kind of huge, okay? So now another formula. Yeah, I know this isn't that fun. A lot of formulas without knowing the whole process. We just have to accept them. But think about it. If I ask you to approve this formula, yeah, so just the application is much easier, right? Anyway, F equals MSR over MSE. So MSR is mean square regression. MSE is mean square error. Okay, So mean square regression is explained part. Mean square errors, unexplained part. This is also proportional rate, right? So if you have a higher F, it's likely to reject the null hypothesis. Okay, so again, F has a two degree of freedom. One, this signifies the number of predictor, and DF2 is total sample size minus 2. So beta 1 equals 0. This is for slope test. And R square, rho square is 0. This is for model test. But since we have only one single predictor, these two are the same. Again, for this model test, we use F-test. For this slope test, we use t-test. Okay. F-test is omnibus test or overall test. And beta 1 test is a slope test, single slope test. 36, slide 36. So F equals MSR over MSE. SSR, sum of square regression. So you can exchange, SSR to MSR when you have only one single X. You cannot exchange these two when you have more than one X variable. Okay. Now we have SPSS output. So ANOVA table is for overall omnibus test. So regression, residual, and total, and sum of square, regression, sum of square error, and sum of square t, total, and DF is for 1, and DF9 is for residual, and 10 is for total. So last time we have a sample 11, sample size 11. So this is n-1 total. And this is predictor 1, okay. And regression, residual is the number, one number is deducted out from this total. MSR, MSE, and F-test is MSR over MSE. And significance means p-value, okay, p-value. So since this is larger than 0.05, so we fail to reject the null hypothesis because this is larger than alpha. And this, if you find this formula, if you find this number F-test value based on the F table, also this is fail to reject the null hypothesis. All right, eventually last slide said, so how do we interpret the F-test? F-test. So our original correlation data, we failed to reject null hypothesis. One cautious expression is you don't say you accept the null hypothesis. That's not true. When you do not have enough evidence to say reject the null hypothesis, you better say that fail to reject the null hypothesis instead of accept the null hypothesis, okay? Because of the falsifiability. Yeah, that's the way how we interpret the hypothesis test. Okay, the value F equals 4.056 would occur more than 5%. So it's hard to ignore that much high probability, 7.5%. That's why we cannot reject the null hypothesis. So that is not too unusual. So we decide the probability these null hypotheses are reasonable. So x has a zero slope. Okay. So if your x is zero slope, that means x does not predict y very well. Okay. So predicted y values do not relate to the actual y. So correlation is zero. The end. All right, next time, let's talk about multiple regression. Bye-bye.